So in the previous lecture, we made some progress towards computing this quantity, where these are arbitrary states and this is some operator, some arbitrary operator. And we showed that this problem maps to computing the vacuum expectation value of three operators, where these are normal ordered operator which we introduced last time. Okay, so in this note that there was no time in the discussion. So in this lecture we will discuss what happens with time. Okay, so we will briefly discuss time and then we will go back to the general discussion again. So throughout the quantum field theory course, we will be using Heisenberg picture. Well, not throughout, so it will be either Heisenberg picture or Dirac picture. But they are same for free theory. Okay, so in the Heisenberg picture, the operator's time evolves. So I write it as I. So this is also called interaction picture. And again, in the free theory, they are all same thing. There is not much difference. Okay, so phi I is this is the time evolution of an operator in the Heisenberg picture. And you can easily compute it, and you can show that this thing simply becomes okay. So this is how the simple operator evolves, and in general you can also figure out how other operators evolve. So for example, compute phi I t power n. Okay, so this is homework. Very good. So then once we have time dependence of the operator, then essentially it's the same thing, right? It's again we now in general we'll be interested in cases of time dependence. In the Heisenberg picture, the states don't evolve, so we'll be interested in computing quantities like this. Now this thing is again, if we follow the same procedure, this is just simply using how to represent an arbitrary state in terms of this. So this will just the discussion in the thing we discussed in the last lecture will simply follow, and this will become phi at 0 power n1 O of t phi of 0 n2. Okay, so we slightly generalize this discussion. And let's say we want to compute just this kind of things. This is all around vacuum, because we know that any correlator around any, so these are called in general correlators. And in general, because of this way we can write down any arbitrary state in terms of the vacuum state and operators acting on that, we can map the problem of computing between any arbitrary state to always vacuum correlation function. So correlator between any two arbitrary state can always be mapped to vacuum correlation. Okay, since we are interested now, so now our goal is to compute okay. So let's now start with the simple example. So in the simplest example, no operator. So in that case, this is simply 1. Then let's compute one operator. And when I compute one operator, let's just choose this operator to be phi of t. And you can compute it to 0 because there is phi of t. Phi of t has either a or a dagger. Okay, so either it will hit to the left. So this thing, how do you do that? So this is h bar power 2m a and this so this acting on this gives you 0, and this acting on this gives you 0, so this quantity is 0. So then next non-trivial thing is two operators. Okay, and again we restrict to, let's restrict to phi of T1, phi of T2. I mean, all these discussions can be generalized to most general operators, but I'm saying just for sake of simplicity, let's go to the simplest two operators, which are this phi of T1 and phi of T2. Okay. This quantity, so we are interested in we are interested in computing phi I of T1 okay. Now you can easily do this computation. So phi I of T2 or phi I of T acting on vacuum is simply gives you, so you have h bar power 2m a exponential I m t a dagger exponential I m t, and this is h bar power 2m exponential I m t on fast excited state. Okay, which means that this correlator simply becomes h bar power 2m. There is a square, so this that thing goes away, exponential minus I m t1 minus t2. Okay, so this is the answer of this quantity, and usually this quantity is written as, just there is a notation, so if this quantity is written in this way. There is a name for this quantity, it is called Weightman propagator. Okay, so in general, 2-point functions, 2-point functions of same operators is called propagator of that operator. Okay, it's called propagator of that operator, and this is this thing is called this is Weightman propagator. Usually people also define, so you see, since it depends on just the time difference, so you just write it as t, and people also define just for later, useful for later purposes, d, and this is by definition, this is definition. Okay, so this is these are that called the two Weightman propagators. Also for useful purpose, for later purposes, it is useful. So these are called position space propagators. And there is also something like frequency space, or in quantum field theory it will become momentum space, frequency space or momentum space. Propagator. and that is defined as the Fourier transform of this. So if I have this quantity, then I can always Fourier transform. So okay, so if you Fourier transform this quantity, then the thing you get, this is called frequency space propagator. Frequency space propagator, and this you can compute for this particular case easily, and this becomes theta of omega delta omega square m square. So this is the theta function. And this is Dirac delta function. So you can compute this thing, and you get this is the frequency space expression for the Weitmann propagator. Similarly, you can compute also the other Weitmann propagator, and this just becomes theta minus omega delta omega square minus m square. So these two things are most important things in quantum field theory, and you will see that almost all other computations can be computations of the Weitmann propagators. Okay, so every computation essentially reduces to computation of Weitmann propagators. There are also many other propagators which we will introduce now. There are other propagators. But all of them can be written in terms of Weitmann propagators. Okay, so for example, the most famous, sorry, not the most famous, let's start from that one. So one is called retarded propagator. And retarded propagator, so we write it in this way, is defined, the definition, there is a theta function in the position space, and the okay, which is same as so this is the definition of the retarded propagator, and this is retarded because this is non-zero. This is there only for later time. So this is non-zero only for later time. That's why it's called retarded propagator. And in the same way, we can also compute the frequency space expression, and the frequency space expression for the retarded propagator is okay. So this is the expression for the retarded propagator. Let me draw this frequency space because it has poles. So in the frequency space, the poles, the location of the poles so if this is the frequency space, Then the poles are, this is also called I epsilon. So this is I epsilon prescription, and you will see the poles are at plus minus m. So let's say these are plus minus m and m minus pi epsilon. So epsilon is always greater than 0. So this is, the poles are somewhere here. Okay, so poles are in negative, lower half plane. Now analogously one can also define advanced propagator. This is very similar to this. So advanced propagator is which is nothing but if you take just the retarded propagator and flip the signs of that. So this is just theta of minus t, vacuum expectation value of okay. So this is the definition of the advanced propagator. You can also do, and this is an exercise, that find the frequency space expression for advanced propagator and show that all the poles are in upper half plane. Last, and actually this is most useful thing in quantum field theory, this is called the Feynman propagator. And Feynman propagator, so in order to define Feynman propagator, it's useful to first define something called time ordering. So what is time ordering of two operators? So time ordering, so if I have time ordering, so this is the notation, this is time ordering. Phi of t1, phi of I of t2. This is same as theta of t1 minus t2, phi 1 t1, phi 2, phi I t2, not phi 2, plus if t2 is greater than t1, then we also have to flip the position of these two operators. Okay, so this is called time ordering, and in the same way, you can compute for more operators. You can compute time ordering for more operators. So for this part, for current issue at hand, the thing we need is basically the 2-point function, the time ordering of 2 operators, and the Feynman propagator is defined as okay. So this is neither retarded nor advanced, this is just time ordered. If you just take the expectation value of 2 fields in the time ordered fashion, then the thing you get is this time ordering operators. And in this case you can easily convince yourself that this becomes from this expression theta 1 minus theta 2. So there is a h bar over 2m, theta 1 minus theta 2 exponential minus m, sorry, not theta, theta of t1 minus t2 exponential minus im t1 plus, so this is theta function, t2 minus t1 exponential im t2 minus t1, which is often written as h bar power 2m. You can just write it exponential because the exponent is always positive. Okay, so this is the expression for the Feynman propagator in position space. Now in frequency space what happens? In frequency space, if you take the Fourier transform, this becomes okay. So check it, show this. Again, epsilon is greater than 0. The interesting thing about this propagator is that if I try to plot in the frequency space, then the poles are at omega is equal to plus minus m minus I epsilon, which means for here the pole is down here and here the pole is down here. So it's neither on, so one pole on lower half plane and other on upper half plane. Okay, and then by choosing appropriate contours, you have to show that this quantity, when I go to position space, this always gives my this expression by exponential im, only the modulus of time appears. Okay, so we will see later the usefulness of this propagator and the usefulness of the frequency space expression also. We will use it extensively. The physical meaning of all these things will probably become clear when we will go to higher dimensions. Then we will try to see what do they mean. But the physical meaning of the retarded propagator and the advanced propagator is very clear. The retarded propagator and the advanced propagator is that one is only non-zero for positive values of t, which means it can only be propagate in future in in the retarded time. Another is just in back in time, so it's advanced, it goes back in time. The expression of the meaning of the Feynman propagator is not at all obvious, but we will see the meaning later when we will do quantum field theory. And this ends our discussions on propagators. Okay, so in the next lecture we will see that how these propagators are useful. So this at this point just looks like a lot of definitions, but we will see that how these propagators are useful if we want to compute. So the goal of this lecture was to compute these quantities. So in the next lecture we will see that how the concept of propagator along with one theorem which is called a Wick's theorem, how it is useful to compute this quantity, and how then it will help us in doing things in quantum field theory.